Hey guys, so we are starting chapter 4 of 1211. It's a chapter all about solutions. In the beginning of the chapter, there's a lot of basic terminology and stuff that you need to learn about solutions. Solutions are homogeneous mixtures. The two components of a mixture, there's always a solvent, which is basically the main component. There's more of the solvent than anything else that's present in the solution. And then anything else that you dissolve into the solvent is called a solute. You can have more than one solute. If you consider like a can of Coca-Cola, the solvent is water. The solutes, there's the sugar, there's the caffeine, there's carbon dioxide, there's all kinds of artificial flavorings and preservatives and all that kind of stuff. So there can be many solutes, but there can only be one solvent in a solution. You can have different kinds of solutions. The air is a solution where there's a bunch of different gases in the air. If you were to consider the solvent of the air, that would be nitrogen gas, N2. And then the solutes, the number one solute would be oxygen, of course. The next gas that is most present is actually argon gas, is about 1% of the atmosphere, and then all the other gases combined are much smaller than that. The only one that can vary a good bit, water. It depends on the humidity of the air. There's a certain amount of water vapor that can exist in the air before it comes together and forms droplets. That's what you would call 100% humidity when droplets start to form. When we talk about solubility, we have to think about which things will dissolve into each other. So there's a general rule, like dissolves like. Again, what that means is if you want to dissolve a polar compound, then it will dissolve best if you put it into a polar solvent. Now, the concepts of polar and nonpolar compounds, we will not fully develop that until chapter 8, chapter 9, when we start drawing Lewis dot structures and all that kind of stuff. For now, for the most part, I'd like for you to know that water is a polar solvent. And then if you dissolve something like sugar, which sugar is a polar compound, if sugar is a polar compound, it will dissolve well into water. So you say sugar is soluble in water. Okay. Compounds that I want you to know are not polar. They are nonpolar, which is down at the bottom here. Nonpolar compounds would be things like hydrocarbons, any molecules made up of just carbon and hydrogen, which hydrocarbons tend to be most of the components of fossil fuels. So gasoline, butane, propane, natural gas, kerosene, diesel, those are all hydrocarbons. None of those will mix with water because they're nonpolar. Water is polar, and solutions typically only form when the compounds have similar properties to each other. Okay, so polar compounds dissolve in polar solvents. We consider like a polar compound, again, when we get to it, chapter 8 and 9, will be a compound where one side of the molecule has more of a negative charge to it and the other side of the molecule has more of a positive charge. So polar compounds have charges in them, which means that if you dissolve an ionic compound into water, which is a polar solvent, most of those will dissolve well because ionic compounds have charges, polar compounds have charges, so that usually creates a good interaction. But not all ionic compounds are soluble. There's actually a list of rules that you have to learn. So in the book, it's called the solubility rules. The next couple of slides have a pretty good summary of the solubility rules, although I'm not actually sure if it's a complete list, so definitely refer to the book. The solubility rules in the book are what you're going to be held responsible for on the test, but you should be able to look at any given ionic compound and tell me, if asked, whether that compound will be soluble or not in water. Okay. For the most part, solubility, it is a funny thing that in this class we're going to focus on whether things are soluble in water or not. In later classes, you'll deal more with the fact that you can have other solvents too, and just because things are soluble in water doesn't tell you anything about whether they're going to be soluble in other solvents. So that'll be something that'll come up in organic, and you'll deal with it then. Okay, for now we're just going to assume that everything is dissolving in water when we talk about solubility. So then we have oil and kerosene and gasoline will not dissolve in water, but since they are similar to each other, they will mix with each other. So I can dissolve gasoline and oil, I can mix them together and they will fully mix. And then whichever one there's more of course, becomes the solvent. So that creates, most people have heard the idea that oil and water don't mix. That's because of the polarity. Now, just to touch one more thing, polar, nonpolar, if you haven't dealt with those terms in that form, which is how chemists would talk about it, those are the same meanings that we use when we talk about in biology, compounds that are hydrophobic and hydrophilic. If something's hydrophobic, it doesn't like to mix with water, that means it's a nonpolar compound. If something is hydrophilic, that means it likes to mix with water, that would be a polar compound. Okay, again, the things that I've said in the last couple of minutes, if you have those things down, that'll be the extent of what you need to know about polar and nonpolar. Okay, but you are responsible for the solubility rules of ionic compounds. So, our solubility rules, again, I'm not going to go through them. You're supposed to learn these, but I'll give a couple of examples. There are rules that apply to cations, which would be the metal ions, and then there are separate rules that apply to the anions. When you look at ionic compounds, sometimes you can look at a rule for both of them, or sometimes if it's like an unusual metal or something, then you're going to go by the rules for the nonmetals, the anion. Okay. So first rule, soluble ionic compounds is ionic compounds that have group 1 metals in them are always soluble. So basically, if I make an ionic compound with sodium, with a group 1 metal, so let's say sodium chloride or sodium sulfate or sodium nitrate, any ionic compound that has sodium in it, it will be soluble based on this rule. Group 1 metals always form soluble ionic compounds. The exceptions are rare, which means that rule you can pretty much apply across the board and not worry about it. Okay, let's go to the next slide, has anions. So if I learn the rule for chlorides, which the same rule applies for chlorides, bromides, and iodides, those are all group 7 elements, they're halogens. So the rule for those is that everything under the list, the list of the top half here are soluble ionic compounds. So basically, chlorides are generally soluble in solution, but there are some exceptions to the rule for chlorides, bromides, and iodides. If you combine chloride with silver, that's an exception where most chlorides are soluble, but silver chloride is not. Silver chloride is an insoluble compound. Also, mercury, this is mercury with a +1 charge, so it's mercury 1. I know there's 2 mercury atoms, but they're paired up. Together they have a +2, so each mercury has a +1. It's kind of a weird ion, but mercury 1 chloride is insoluble. And then lead with a +2 charge, so lead 2 chloride, also insoluble. Those are the only 3 common chloride compounds that could be insoluble in solution. So if you mix silver ions in solution with chloride ions in solution, if they're in the solution together, they're going to come together, form a precipitate, and drop out of the solution as a solid on the bottom. Okay? All right, now, when we dissolve ionic compounds, again, they're going to talk about this in a minute, but water itself is not a good conductor of electricity. Okay, it's considered to be more of an insulator than a conductor. Now, if you're in the bathtub and you drop, a hairdryer in the bathtub, electricity, if it's a strong amount of electricity and a short distance, electricity can pass through water somewhat, but it's not a good conductor. Okay? Now, anything that you dissolve into water that makes it more conductive is called an electrolyte. And the compounds that tend to do this are, first of all, soluble ionic compounds. Okay, now, specifically soluble ones, because if you add an insoluble compound to water, it just settles to the bottom. It doesn't dissolve, it's not going to change the properties of the water. So, if you have an ionic compound that is soluble, it's going to increase the conductivity of that solution. Also, if you dissolve a strong acid, Now, I told you there's a few acids you're supposed to know. The strong ones, hydrochloric acid, nitric acid, sulfuric acid, those are all strong acids. Phosphoric acid and acetic acid are weak acids. So basically, we have a setup in the lab that you'll use in 1212 where we have a light bulb that's mounted on a piece of wood, and the wire that runs to the plug, we've cut the wire, cut it in half, and then we've exposed the metal wire and stuck it down like this. And then we have it set up so that if you have a beaker of a solution and you bring it up under the two wires, if the solution is a good conductor of electricity, then it'll basically reconnect the wires by allowing the electricity to pass through the solution, and then the light bulb will turn on if you have it plugged in. So these are the compounds that if you dissolve them in water will make the light bulb turn on, because electricity can pass through the solution well. Okay, so if I dissolve salt in the water, sodium chloride in the water, and then put it up to that light bulb, it will conduct electricity and light up the bulb. If I have a hydrochloric acid solution and bring it up under the light bulb will turn on. Okay, now if I use a weak acid, and all these compounds, what they do when they dissolve in a solution, they break up and give you ions in solution. Strong acids produce a lot of ions, which is why it'll light up the light bulb. A weak acid will produce a few ions in solution, just not as many. So if I bring that up under the light bulb, sometimes the light bulb will come on a little bit, but it'll be really dim instead of bright. So weak acids are called weak electrolytes. The ones on this list are going to be called strong electrolytes. They fully ionize in solution, they produce a lot of ions, they allow the conductivity to increase dramatically. Weak electrolytes increase the conductivity a little bit, which is like why I said the light bulb might come on a little bit, but not full brightness like we would expect. All right, and then we also have strong bases. Strong bases tend to be metal hydroxides, like sodium hydroxide, potassium hydroxide, and so on. Well, honestly, strong bases are part of the category of soluble ionic compounds. Like sodium hydroxide is a soluble ionic compound, and it's a strong base. So really, if you're trying to learn your electrolytes, the first two bullets are the important ones to learn. The third one is already covered within the first bullet. All right, so when we dissolve sodium chloride into solution, the crystal structure comes apart. I have a video that I'm going to switch over to and show real quickly. So essentially this video, the picture I'm showing, this is a crystal of sodium chloride where the white spheres with a positive on them, that's the sodium ion. The negative on the green atoms are chloride ions. So a crystal of sodium chloride, which the formula is NaCl. If you remember, that's the empirical formula for sodium chloride. Basically, every crystal of salt that if you have a salt shaker, pour some in your hand, every crystal has millions and millions of sodium ions and chloride ions mixed together in a crystal lattice structure. It's a very organized structure where the positive ions are surrounded by negatives, the negatives are surrounded by positives. The best way that they can arrange themselves is how the crystal forms. Okay, so we have a single crystal of sodium chloride. It's a 1-to-1 ratio between Na plus and Cl minus, which is where the formula NaCl comes from. And then when I dissolve it in water, so if I drop a crystal into a beaker of water, what happens is the water molecules, which this is an oxygen with two hydrogens on it, so that's a water molecule. The water molecules come in, and if I start playing the video, they come in and they pull the ions apart one ion at a time. So some water molecules will pull out a chloride, another set of water molecules will pull out sodium, and the water molecules surround the ions to stabilize them. Okay? Now, as we go further into chemistry, when we get to Lewis dot structures and stuff, it's actually the water molecules surround the ions in a very specific way. The chloride, a water molecule, is a bent molecule. It's got the oxygen and the two hydrogens are kind of both on one side. The oxygen is more electronegative So it's a polar molecule where there's a negative charge on the oxygen, and then the hydrogens have more of a positive charge. So what happens is all the waters around the chloride ion, notice they've turned themselves so that the hydrogens are closer to the chloride, because the positive of the hydrogens and the negative of the chloride attract each other. So all the water molecules have turned so that the hydrogens are close to the chlorides. If I look at sodium, it's the opposite. The water molecules have turned, so now the oxygen is closer to the sodium ion because the negative on the oxygen and the positive of the chloride attract each other. So this is how ionic compounds dissolve. Number one, the biggest thing is that the ions from the crystal that were together, when they dissolve, they get separated out, and I form these separate ions in solution. And this is the key for when we talk about an electrolyte. Electricity is a flow of electrons through a solution. Electrons are charged particles. So in order for the electrons to flow through the solution very well, there have to be other charged particles in there to interact and kind of stabilize that flow of electrons. So a water molecule has what we call partial charges. I mean, actually it's a little bit charged, but not really. But then when we dissolve an ionic compound, they're fully charged particles. They greatly enhance the ability of the electrons to move through the solution, which is why it's a strong electrolyte. Okay, it's a good point to cut off for this video. We'll start another one.